Okay, so for the last talk of the morning session, Jacob Tsimerman will give the first lecture on Hodge theory.
Great, thanks very much. How it sounds? Things okay? Okay, great. Yeah, so I'm going to try to give at least today, a gentle introduction to Hodge theory, sort of what the ideas are, what the point is, and then the goal of the tutorial, sort of going forward, will be to explain a little bit of how Hodge theory and homonormality sort of play together. I'll be using a lot of what Tom has been talking about in his lectures, but right now, there's going to be very little homonormality in good stock. And the idea of Hodge theory, or at least the way I'm going to approach it, is you want to study complex algebraic varieties. Using as much as we can linear data. So complex algebraic varieties are very hard, the moduli are very complicated. We're going to try to get as far as we can using complicated but still linear information. So what does this mean concretely? Well, for our setup, let's take X, the smooth, projective varieties over C. You don't need smooth and projective for almost any of what I'm going to say, but I'm almost always going to assume it because it makes things a whole lot simpler. And now to X, we can assign a few different structures. So we can assign Betty cohomology. So given an integer n, we can just look at topological space given by the complex points of X. We can take the cohomology with Z coefficients or with C coefficients. Now, Z coefficients are going to be important for us, and this in general might have some torsion inside it. It's not always going to be a free abelian group. We're almost always going to ignore that. So we're almost always going to look at this group, sort of mod torsion, and we're going to call it the free part of the group. So some free here. I mean, we're ignoring any of that stuff. So we get some lattice. Likewise, we can assign the round cohomology to this group, which I'll write as xn hn the round of x comma c. And the simplest way to think about this is just closed n-forms mod exact n-forms. So another topological, if you like, invariant. At least for now, we'll think about it that way. Then we have the round isomorphism between these two guys, between Betty and the round cohomology. And how does this work? If we have a cohomology class gamma, and we map it to the class of some omega, then for all homology classes, you want gamma on M to equal the integral of omega over M. Give you an isomorphism of homology groups. Okay, so far, this is great, but there's no moduli here. So far, I'm just giving you vector spaces of a given dimension with some isomorphism between them, and I'm giving you a lattice inside one of those vector spaces. So that information, thought of abstractly, doesn't vary continuously. And what we're really trying to get at is some sort of theory built out of linear algebra where you do have moduli. You can study sort of changes of varieties and families. So to do that, what we're going to do is we're going to refine the de Rham cohomology groups further. And we're going to use the holomorphic structure for that. So locally, if we have some coordinates, z1 through zb, are holomorphic coordinates. We can use that to, instead of just talking about n-forms, split it up into holomorphic and anti-holomorphic components. So we say that omega is of type AB, or an A comma B form, if we can write omega as a sum over sets I of size A and sets J of size B of the wedge product of the DZIs together with the DZJ bars, multiplied by some function. There's no condition on this function. This function can be, say, any smooth function. And it wouldn't even make sense, by the way, to say this function is holomorphic or something, because we have DZ bars here. So if we make changes of variables, that will sort of change things up. Nonetheless, we're just using the sort of splitting of the tangent space to make this definition. And so it's not hard to show that this definition is invariant of which coordinate you pick, and that you can write every form uniquely. Every n form is the sum of AB forms for varying ABs. So give you some kind of split. Okay. That's all well and good. Things get much harder. I remember. If I write over here, this is like the corner of death here. Then avoid this now. Things get much harder if you want to use this to descend down to cohomology, simply because if I apply B to a pure form, a form of type AB, I can get something of type A plus 1B and something of type AB plus 1. So it doesn't play super well with purity. Nonetheless, we have what's called the Hodge decomposition theorem. Which says that if we have smooth projective varieties, then in fact things are very nice. What we can do is we can define HAB, or HABX, let me say, inside the de Rham cohomology of X, the A plus B of de Rham cohomology of X, to be guys which are represented by, so the span of closed AB forms. We can define this in general. It's going to give us some vector subspace of cohomology. But the theorem is that, in fact, if we then look at the Rham cohomology, it splits as a direct sum over A and B's that sum to n of HAB of X. Okay, so this is very much not free. I want to emphasize that. If you take a general compact complex manifold, this is going to be false, even though you can define these types and such. You need weaker conditions than smooth projective work. You can work in Kähler geometry and prove this theorem as well. But I want to sort of make it clear this is a deep result. And it's not hard to start playing and understand that it's a deep result. It's sort of the obvious arguments don't work. You need something, you need some extra ingredients. Okay, and the point here, the reason that this is so exciting is because now all of a sudden we do have a modular. And let me explain how rather emphasize that that's true. Oof. Maybe the red was a bad idea. Okay, so now given a smooth projective variety and a number n, what is the kind of data that we have recorded? Well, we have a free abelian group of some rank sitting inside this complexification. Sorry, let me be precise and try to not make as many mistakes as I usually do. This is better cohomology. So let me actually talk about the group of points X sitting inside his complexification. Sorry? Oh, the sub free means I'm quoting out. Okay. Yeah. So I don't want to pay attention to it. Even though you can, that gives more information, but I'm going to be lazy. And this is isomorphic this way to the round cohomology, which itself is actually equal to this direct sum decomposition, HAB of X. And now we can think of this abstractly as a lattice complexification and this kind of direct sum decomposition. And this sort of obviously has moduli. Why obviously? If we forget about the lattice, then this does not have moduli, even with some more conditions I'm going to put on. There's a unique way. All direct sum decompositions of vector spaces are sort of abstractly the same. But once I fix the lattice, then I really take away your ability to do automorphisms. Automorphisms drop from GLC to GLZ. That's a discrete countable group. So we have some dimensional space here, mod some countable group. We're going to get something with dimension. Okay, so this is now a meaningful sort of invariant. You can associate to a variety. Another way to think about it is if you pick a basis here, you can ask what coefficients do I have to throw in order to get into one of these guys. Of course, it depends which basis you take, but you still get a lot of information there. Any questions so far? Okay. Okay, so let me now make a whole bunch of observations regarding what we just did. So the first one is that you may have noticed I didn't write an x of c over here, just an x. And this plays an important role in some arithmetic questions. But the round cohomology, even though it has this description topologically, it can be defined algebraically. So I'll say a few words about why in a minute. It's not so important you remember or understand those words I'm about to say. The most important takeaway is that you can do this in some way. And that's very useful because the way to think about it then is if you have an algebraic variety, you can assign this algebraic invariant of the round cohomology. And then by picking a complex embedding of your base field, you then get this transcendental notion of the Betty class. So even though sometimes the way it's thought of is like you have a lattice and then you tensor it with C and decompose into vector spaces, really the more canonical thing is you have this direct sum decomposition, and then the transcendental piece of data is sort of this abelian group sitting inside it. Kind of minor points, but they become a little important later on. So let me say something about why this can be defined algebraically. Yeah, let me say something about why it can be defined algebraically. So the way to think about it, I realize I'm preparing this talk. I wish I knew a better, sort of simpler way of explaining this, but here's the only way I know how to do it. So if you look at the round cohomology, the way we think about it, of closed n forms not exact, you can think about it as the hypercohomology of the following complex. This is analytic. Sorry, it starts at 0. It starts at 0, goes to 1, and keeps going. So we have this complex of sheaves over the analytic topology. we can define hypercohomology through spectral sequence or whatever, some algebraic tool, and that will record for you the round cohomology of X. Now it turns out this is naturally isomorphic to the same thing, but done algebraically. So without the analytic topology, just working in the heuristic topology. This is due Dick. Then, in fact, more than that, if you're in this smooth projective case, this is naturally isomorphic to the direct sum over A plus B equals N of the eighth cohomology of omega B. Again, it's very nice kinetic. And there's a way starting from a cohomology class to sort of give you a form and such. I'm not going to go through it because this is just a note, prevents me from having to do any work. But the point is that not only can we define round cohomology algebraically, but this splitting we had into AB type forms, you can read off very directly from this algebraic description as just this group over here. Okay. So again, one very nice consequence of this, like the reason you care about the algebraic definition, is if you take a variety over a field, say a quadratic field, and you look at its two complex conjugate, and its two complex embeddings, if it's a real quadratic field, then the complex varieties you might get could look very different. They can look very different topologically. Nonetheless, this is sort of defined algebraically, so you can identify that they're on. Okay. That's the first thing I wanted to say. Number two is what happens if B equals 0. So if we look at H of n comma 0 of X, then in fact, this is just closed holomorphic n-forms mod exact holomorphic n-forms. And because we're in a smooth projective variety, holomorphic is the same thing as algebraic in this case. So even though we have a very transcendental tool we're working with, this sort of little piece of it is in fact highly algebraic. Okay, why is this true? Well, I'll give an example proof in the case of n equals 1, from which you can sort of do a similar computation to get the general case. Just to give you an idea, suppose we have a form f of z dz in one variable, which is closed. That means d of it is 0. And this is what it's df by dz dz wedge dz plus df by dz bar dz bar wedge dz. This vanishes automatically. This does not, and so this guy has to be 0, which exactly means that you're holomorphic. This follows directly from the definition, which is very nice because we didn't put any holomorphicity assumption at the beginning. We end up with this very clean description. And the same thing works for arbitrary. So somehow this story, of course, one thing you can assign to a variety is global n-forms. And this story somehow generalizes that. It puts it into this much broader framework. Okay, the third observation, which is very simple, that H of AB is just the complex conjugate of H of BA. Just because if you take the complex conjugate of like B for all the DZs become BZ bars and vice versa. And closeness isn't affected by taking complex conjugates.
Can you explain this?
Can I explain this identification in terms of this? That's a great question. Just think very briefly if I can do that easily.
No, you can't.
I can't. Okay, great. I thought I could. Apparently I can't. So it's not one thing you can see without too much hand wringing.
But this is an isomorphism. I mean, actually, these are the graded parts of the filtration. It's not really
Yes, I'm
the
cheating.
identification of the HP omega Q with HPQ is not obvious. It's not an embedding.
There's some subtleties going on here.
So this is really a filtration.
There's really a filtration, yes. We talked about
So the filtration is algebraic.
Right.
The filtration is algebraic. Those coefficients are algebraic, but the HAD are not algebraic.
Absolutely, yes, absolutely. Which sort of the complex conjugate gives you a hint though, because that couldn't be true. Nonetheless, you can say something, I think, which may be informative, which is the dimension of these two are the same. And that follows by Serre duality, because omega b and omega n minus b pair together to give you omega n. So you can say that, but otherwise, yeah, no naturalism. Great. Okay, the last thing that I want to say before saying even more stuff is something about bilinear forms. And then we'll move on to some concrete examples. You can see how the sort of big machinery looks in some very specific cases. So far, we actually haven't used the fact that X is projective at all. We just use the algebraism from it. But being projective means you're actually inside Pn essentially. So what we can do is we can take X as actually sitting in Pn, and we can take H in X to be the intersection of X with a hyperplane. And that gives us some complex codimension 1 subvariety of X, which in particular gives us an H2 class because complex manifolds are naturally oriented. And so we can think of the productivity as giving us a very special type of H2 class inside X. This should be X of C, but I'm going to send you lazy, not writing it. And on the other hand, you can use the Poincaré, the Durand isomorphism to write this as the cohomology class of some 2 form. And in fact, this 2 form sits inside H11 of X. So we have this very special H2 class. And now what we're going to do is we're going to use this H2 class to define a bilinear form on our cohomology groups. And the way this works is the following. I want to remind you, first of all, that this isomorphism, there should be classes here everywhere, of Durand respects the cup product very nicely. So if A and B are cohomology classes corresponding to forms omega A and omega B.
It's AB are not the parameters.
No, oh no. Thank you. They are not. Let's give them different names. Let's call them cohomology class 1 and cohomology class 2. Thank you. Then this respects the cup product as the exterior product on the differential side. A good sanity check is they're both symmetric with the same sign as they should be for this. And now what we can do is if A and B are inside. Yes. Thank you. If C1 and C2 are inside k cohomology group of X, what we can do is we can define Q or QK sometimes, right, of C1 and C2 to be the cup of C1 together with C2. That will land us an H2K. And now we're going to further cup this with the class of H, the power of the dimension of X minus K. This will put us inside the very top cohomology group, which is, in fact, which is isomorphic to C. And in fact, I've been writing C's everywhere, but I can replace this with Z as well and get the same result. So I get a bilinear form, which is actually defined over Z. And now this really depends on my projective class. And of course, if I do it on the form side, I just replace this with the wedge product and then wedge with a sufficiently high power of my polarizing form, and I integrate that over the entire variety.
Before you erase it, for thing 2, like right above you, can we just erase that non-exact homomorphic endpoint?
Can we erase it?
Yeah, just because I mean, it follows from the thing just below it, like the direct sum decomposition. The exact homomorphic endpoint is 0.
Oh, yes, of course. Thank you. Thank you.
So I'm just
No, you're right. Of course. Yeah, thanks. Any other mistakes? I mean, that are very visible, comparable?
It's still
Okay.
true.
Sorry?
It's still true.
One word.
It's still true.
It's still true. It's true. It's not technically a mistake. It's more of a test.
We're going to take.
Absolutely. Okay.
But it's a suspense because I was waiting for it to get erased. And then
Yeah.
suspense.
That's right. Okay, so this form behaves very nicely with our splitting. So if I write Q of H of AB, H of CD, now I'm allowed to use this AB again of X, where their sum is the same. But this is actually 0 unless A is equal to D. So you sort of have to flip. You want to pair something with its conjugate, essentially. Oh, sorry. And now what I can do, and I don't want to spend a lot of time on this, so I won't, but I can find a piece, well, I guess C, Z or C, doesn't matter, of the cohomology, a natural piece here, such that if I take V inside H of AB X primitive, so which lands inside this guy, then Q of V with its conjugate, I to the power of A minus D, is bigger than 0. I get this nice definite condition if I restrict this primitive part of the cohomology. We sort of built topologically out of this H2 class we have here, but there's some combinatorics there, and I don't really want to spend time on it, even though it's not particularly deep. But to get what is actually a Hodge structure, which we haven't defined yet, but will be very shortly inspired by all this information, it's sort of natural to restrict this primitive part. Okay. Now let me write down some examples. So we have some concrete ideas of what these Hodge structures are and what they can do. See?
What is the bar?
V bar is just the complex conjugate of the class. It's a, I'm just thinking of the form. I'm just conjugate the form. This stands for comma. Or if you want to think topologically, just literally conjugate the coefficients. All right, so the first example, the sort of best one to keep in mind still, is elliptic curves. So instead of working algebraically at all for this example, I'll just work complex analytically, because that's where all the relevance to the structure is coming in. So I'm going to think of my elliptic curve as C mod L, where L is literally the span over Z of 2 points, which I can then scale one of them to be 1. Sorry, Z. Okay, so I multiply by rank 2 letters and you get the curve in sort of the usual way. Maybe I'll draw a little picture here. Here is 1. Here is Z. And I'm looking at the quotient here. Okay, so then the homology of E with Z has no torsion in this case. It's naturally isomorphic to L, where the isomorphism just sends an element L to the path from 0 to L, descend it down to elliptic curve. The cohomology of E with Z coefficients, it's naturally the span of 2 elements E1 and E2, where I'll pick them such that E1 just sends the class of 1 to 1 and the class of Z to 0, and E2 does the opposite, and the class of 1 to 0 and the class of Z to 1. Now we're going to work in rank 1, so the first homology group. So we only have H10 and H01, and they're complex conjugates. So to tell you decomposition, it's not to tell you what H10 is. H10, as we already saw, is just closed holomorphic 1 forms. And we have a very natural closed holomorphic 1 form here, which is DZ. DZ descends down. So H1, the RAM of E with Z coefficients, is isomorphic to H10 plus H01 bar plus H01, which is its conjugate. And these are spanned by, this actually equals C times the class of DZ plus C times the class of DZ bar. I'm sorry?
It's not the same.
Oh, it's not the same Z. You're right. Yeah, let me make this a tau. Just to. Sorry, somebody just explained dissatisfaction. That's very sensible. Okay, I think that's all I have to change. Thank you. Let's make Z the coordinate and tau the actual complex. Okay, so then under this isomorphism, let's see what happens. Well, DZ, class of DZ rather, gets sent where? Well, it gets sent to the cohomology class represented by integrating DZ. If I integrate DZ from 0 to any number, I get that number. So on 1, I should get 1. So it's E1. And then on tau, I should get tau. So plus tau E2. Likewise, DZ bar, it's sent to E1 minus tau. Sorry, so by DZ bar gets sent to E1 plus tau bar. Excuse me. Okay, so that's our Hodge structure. It's extremely expensive. Now what I want to show is how in this setting of elliptic curves, you can actually recover the elliptic curve entirely from the data of the Hodge structure. Okay. So entirely from this data here, we're going to recover the elliptic curve. So recover in E. And we do that in a very simple way. We just write down the first Durand cohomology group of E. And we're going to mod out by H10 as well as the image of our lattice. So H1 E comma Z. So I'm no longer running the isomorphism to just interchangeably going between topology and Durand. Very cohomology and Durand cohomology. Okay, so let's consider this quotient. Well, we can think of this as the span of E1 and E2 over the complex numbers. And we're modding out by H10, which is the span of E1 plus tau E2 over the complex numbers, together with a span of E1 and E2 over Z2. Okay. So I'm going to use this quotient to eliminate the E1 variable, because E1 is minus tau E2. And I get the span of E2 over C. Mod. Now over Z, I still have E2. And E1 in the quotient looks like minus tau 2. But what is this now? This is exactly my elliptic curve multiplied by E2. That's exactly C mod the span of 1 and tau. Okay, so in this case, our linear algebraic data is actually enough to recover the full elliptic curve. I don't end in 5 minutes, do I? Am I crazy?
It's not crazy.
I am crazy. Quarter past. Okay, thank you. Great, fantastic. Okay, so in this case, which is admittedly very rare and special, but still illustrative of the point, this is a complete invariant. So all the stuff we do to explain why the modular curve parameterizes the elliptic curves can be done in the same way, but under the more natural mantra of Hodge theory, where you just classify the Hodge structures. They are given by linear algebraic data, so it makes sense you're doing it linear algebraically, and you get this result. Okay, let me do one more example. Okay, so one more example, which in some sense maybe is more of the same, but I think it illustrates some nice properties. I want to give it anyway. So take C to be a genus G curve, G at least 2. Not that I need G at least 2, but let's take G. Actually, G at least 1 is already right there. But morally, I want to take G at least 2. And now do the same thing, a little less concretely. So we'll let gamma 1 through gamma 2G be a symplectic basis for H1. See? So gamma 1 through gamma G pair with gamma G plus 1 to gamma 2G in the usual way. We'll let E1 through EG and F1 through FG be the dual basis in cohomology. And we just let omega 1 through omega G be a basis for 1/4. Polymorphic 1. Okay, so by a curve here, I mean a smooth projected curve, by the way. Things can still be done for affine curve, but they're more complicated in a way that I might talk about in maybe lecture 3. Okay, so now things less explicit, but we still have our isomorphism, which sends omega to the sum from 1 to g of omega integrated over gamma I times ei plus the integral of omega integrated over gamma I plus g times fi by the same computation. Now what I want to show is how if we form the same quotient here, we don't recover the curve, of course, because our curve now is not a group, but we recover the Jacobian of the curve. And of course, you can make a more general story for abelian varieties, which is definitely worth knowing. But I think this case is nice in sort of another way. And the Jacobian has a very nice geometric description. So how to think about this? Well, the way I want to think about it is the following. If you look at beta cohomology, then because of the symplectic pairing, this is isomorphic to the dual of beta cohomology. And because of our de Rham isomorphism, this is isomorphic to the dual of our de Rham cohomology. I'm omitting C because we only have one variety we're working with. And how does this work? Well, EI here maps to FI by the nature of our symplectic basis. And FI maps to the dual form, which sends omega to the integral of omega over Fi. And Fi maps to negative EI, which maps to omega maps to the negative integral over gamma I. Gamma I plus G, integral over gamma I of omega. We have these isomorphisms. So as a result now, if we look at H1 Betty, mod H1 0 plus H1 Betty with Z coefficients. So same coefficient we did over there. And now we reformulate it as this dual thing. Well, we look at H1 de Rham dual, but we're modding out by H1 0 here, which under the pairing is the full dual to H01. So in fact, this quotient here under the dual isomorphism, under this map here, just maps to H1 0 dual. And where did this H1CZ goes? Well, we see here what our classes do to forms. It mods out by all the classes given by omega maps to the integral over gamma I omega over Z. I goes from 1 to 2G. And this is exactly our Jacobian. The usual description, right? We're looking at all functions on one forms, mod out by periods. These are all the periods that we have. So, okay, in some sense, it's a very classical story here, but I think it's nice to see it in the language of Hodge theory. We can also, I'll just mention, I'm not going to do it. We, of course, have a quadratic form here that I've been ignoring. And if we translate it here, we see the polarization of the Jacobian in the usual description of polarizations of complex abelian varieties through quadratic forms. But I don't want to get into that. All right. So now let me actually give you the definition of a Hodge structure, which is exactly made to capture all the structure we saw present from smooth projective varieties. So a polarized, and we're only going to think about polarized Hodge structures. Hodge structure of weight n consists of the following data. First of all, L, which is a free abelian group of rank n, which you could say z to the n, but it's more sort of natural to say this. A bilinear form U on L, which is -1 to the n symmetric. So if n is even, it should be symmetric. If n is odd, it should be asymmetric. And finally, a decomposition L over the complex numbers as a direct sum over a plus b equals n into this pieces LAB, such that, so of course, this is just some discrete data over here. All the real sort of the bulk of the information is contained here. This is where all the moduli lies. First of all, LPQ is LQP bar, just like before. Then you have orthogonality. Q of VW is 0. V is an LPQ, W is an LRS, and P is not S. So everything only matches pairs with its opposite. And finally, we have this positivity, very useful. If you send V to either the P minus Q, there's this weird sign. But again, it just comes from the geometry. Times Q of VV bar. This is, sorry, I'm not sending anything anywhere. This is positive. V is an LPQ and is not 0. We have this positivity. This is very important, this condition. This condition essentially makes the moduli theory reasonable. And it does this basically by cutting down your automorphism groups so that all the resulting quotients become topologically sensitive manifolds. You should think of this as analogous to, by the stuff we just saw, the polarization of the Bilinear variety, without which the moduli theory would not be well behaved, because you would have too many automorphisms.
So this Hodge structure doesn't have to come from anything, if we are.
That's right. It doesn't have to come from anything, and as we'll see, the vast majority of these don't come from any complex varieties. So you get this very funny story, which I'm going to talk about more in the next few lectures, of you have this sort of complex moduli of stuff, inside which lies a jumble of algebraic information that's kind of hard to recover. Okay, but that's the data.
When you said earlier that you can't recover the curve, a general curve from the Jacobian, that's not actually true, right? In theory.
Oh, no, that's not what I meant. I meant that there's no correspondence. I probably misspoke. So for elliptic curves, an elliptic curve is the same data as the rank 1 Hodge structure. For curves, it's not true because you have abelian varieties that aren't Jacobian. Of course, you're right. You can recover the curve. Yeah, not with the construction I gave. You got to do some work. It's some theoretic theorem, but you can do it. You're right, absolutely. Okay. So, what we'll be largely focused on, and where homonymality sort of comes in, or at least these two subjects touch each other, is not focusing on an individual Hodge structure, but a family of Hodge structures. Much like you have a family of varieties, they all have Hodge structures. You want to know how that changes. With a family, you get functions which are, of course, transcendental. Well, not of course, but they are usually transcendental. But you want to control them somehow, and that's exactly where homonymality sort of plays a role. So next time, yes.
Yeah, like in a Hodge structure for a curve,
Yes.
then we want L to have rank like 2G or something?
Sorry. Ah. 3 abelian group. There's no rank. Yeah. I apologize. Thank you. Thank you very much. I overuse the letter N. Anyways, thank you. So in future lectures, we'll talk about.
Oh, yeah, it's then.
No, this N is correct. This N is based on the weight, yeah, which relates to the indexing. Yeah, that N is right. Yeah. So in future lectures, we'll talk about families of Hodge structures. And yeah, maybe right now, just in preparation for that, another corner of that. We won't talk about families, but we can already, just with information, classify the set of all possible Hodge structures. So let's say something about moduli. To give a moduli problem, you have to sort of zoom in to the kind of Hodge structures you're looking at. For example, you almost certainly want to fix a weight, but in fact, it's very convenient to think of this as, well, let's fix L and Q. Let's fix at least the isomorphism type of L with Q. That's some discrete data. And then let's think about all the possible decompositions we can put here. Yeah, in order to get this Hodge structure. So, in that vein, let's let G be the automorphism group of LQ. Thought of as an algebraic group, so I can put any coefficient group here. But essentially, G is some sort of either orthogonal or symplectic group, depending on the parity of n. We'll let D check be the set of all decompositions of L into direct sums of LPQ, where LPQ is LQ P bar.
Usually check in the compactable, right?
That's correct. I'll write something which I think is sensible, then maybe you can just give me a few minutes, and then you can ask your question.
So not L, Q, and N are fixed.
So I'm fixing L and Q, given an L and Q, and an M, that's right, yes. Let me write that down. So fix the triple LQN. So I want to get all the moduli stuff here. So I'm going to get the complex conjugacy, and also I want the orthogonality. So satisfying orthogonality. So satisfying two, I'll just say. Okay. Now inside D check, which is indeed a compact dual, I have some space D, which turns out to be an open subset. So D is everything which satisfies positivity. And now this gives me every single Hodge structure, just by fiat. I just defined them all. But of course, if I care up to isomorphism, then L and Q were fixed, but I can change LQ by an automorphism, which will act on this set of possible Ds. And so the moduli space is D mod GZ. Okay. And it turns out this is a sort of a nice, well-behaved space in some ways. So one, well, maybe I'll save that for next time. So maybe let me end here. Let me just say that one thing which is not clear from this description is why D is a complex manifold. And relatedly, something which is not clear from the definition of a Hodge structure is how to consider them in families, because this complex conjugacy condition is inherently non-holomorphic. You can't have complex conjugates with holomorphic stuff. And so next time we'll address both of those. We'll explain how to replace this condition by a filtration, which will allow us a complex interpretation. And we'll use that to start studying families of Hodge vectors. All right, I'll stop here for now. Thank you very much.
Maybe first. So for Greg's thing, I think with recheck, if you do it that way, like for the elliptic curve case, you're gonna wind up taking out no, not the infinity, taking out the line equator.
Yeah.
You would wind up taking out P1R. I think if you do it, I mean, I could be wrong, but I think you wind up taking out the places where L10 is.
You're right.
real.
I understand your concern. You're right.
Yeah.
You're right. This is slightly wrong.
We
Yeah.
don't-
I'll fix it next
we
time. You're correct.
don't wanna do- Yeah.
Other questions or comments? Okay, thank Jacob.